Okay, welcome back. This is our last lesson together before you take a week's break for intersession week. And after intersession week, you'll have our Professor Vadut teaching you. So, this lesson is going to be a pretty long one and probably the most challenging of all the lessons. Chapter 6 really is just 20 questions that are on the medium to hard to potentially extremely hard for some people. I'm going to just review some formulas from trigonometry, basically some area formulas for circles, sectors, and triangles, and then I'll get into the examples. Out of the 20 questions that are in Chapter 6, look for solutions to, I believe it's 11 questions that I'm covering in this lecture. So, I'm not sure how long this video is going to be, so if it gets on the longer side, I'll stick to some of the tougher questions. Okay, so let's just talk about some of the formulas for areas of triangles and sectors. Some of these you know, and some of them may be new or interesting for you to see. So there's your classic formula for the area of a triangle. This one's useful, of course, when you know the base of the triangle. Let's say you know the base here, and you know the height. Now, I don't care if this is a right-angled triangle, but I do know that the height is perpendicular to the base. That's the one that you've known probably the longest in your life. Here's another variation on the formula where we can use the sine ratio. This is a situation where you have what's called a contained angle. So we will be using this in the first example that I cover in today's class. So for example, let's say that this is 5 and this is 4. And let's say this angle here is 29 degrees. See how the angle is contained by the two sides? The area is simply going to be half 5, 4 sine 29. I'm going to put some brackets there. But that's an example of how you could use this formula. So again, this formula is going to be used for the first exercise that I cover with you. Here's another formula called Herons Formula. This formula will be brought up in Chapter 7 when we talk about surface areas and volumes. I'm the author of Chapter 7, so I do know for sure that there are many examples in there that use Herons Formula. This is an example where you would use the formula when you have three sides on a triangle given. So for example, let's say that, I'll just squeeze it down here, let's say that you had a triangle like this, and this is 4 and 5 and 6. Well, if you know the side lengths only, and assuming the triangle has a feasible lengths, then you can actually find the area. You can find the area based on the side lengths. This formula has been around for a very long time. I know references at least 1,000 years old, so you can definitely enjoy that formula in the next chapter. I'm not going to use it in today's lesson though. Also, we have the area of a sector of a circle. An area of a sector of a circle refers to when you have a circle and you draw something like that, like a pizza slice if you want. So if you want to find the area of the sector, you can use this formula. Notice that I've given the formula in degrees. The formula in radians is much more elegant, but for this course, all measurements and angles and computations are in degrees. So if you want to see the formula with radians, you can definitely look it up online. And I have summarized it here, but I haven't shown you the derivation. But you can see definitely that there is a much more elegant form. So in this case, really it's just what fraction does this angle have relative to 360. So is it half of a circle or a tenth of a circle? You can base it strictly on the angle, whereas this one's based on the idea of an arc length and the sector relationship. So interesting formulas. These sector formulas, I won't cover them in any examples today off the top of my head. I'll be sticking to ones that involve mostly Pythagorean theorem, sine, cos, and tan, and triangle areas. So let's get going on our first example. So if you look in the notes, we have a question 2. I didn't present a list of questions that I'm covering at the beginning of the video. However, any questions that I do skip, definitely, if you're interested in solutions to them, There are the final answers in the back of the notes, but also you can email me and I can definitely send you a picture of any of the answers that you're interested in. I just want to say I'm not dodging the hard questions and doing the easy ones here. I'm doing the well-balanced mix of easy, medium, and hard questions. So in this first example, we're talking about what percent of a full circle does an inscribed pentagon take up? And I should mention the word regular here. And in the second question, as a follow-up, what percentage of a full circle does a regular octagon occupy? So I'll just squeeze an image here. So let's say that you have the circle here, and you put a pentagon inside. So the idea is like, what area, what fraction of the circle does that pentagon take up? So usually in class I'll ask this, and I get all kinds of answers like half or 3/4 or whatever. And then the bigger question I have for students is, if you try to squeeze an octagon, I'm going to count to 8 here. I'm going to probably fail anyway, but there's supposed to be 8 sides there. I'll just put an 8 here. Do you think the octagon occupies more area than the pentagon or less? And of course it's regular, so did I count it right? Whatever. It's all good. Anyway, the answer intuitively would be that the octagon should cover more. The more sides that you have to the figure, the more the percentage that it's going to have closer to 100%. Notice that there's no numbers in this question. So maybe you can take the recommendation here that you can assume that the radius is like 1 meter or 10 meters or just a nice, easy number to work with. So I'm going to turn off the video feed at this point and actually answer the question. So for the inscribed regular pentagon, I'm not actually interested in making any assumptions about what the radius is. If you like, you can let r equal 1, whatever units you want, 1 meter, okay? So if that makes you feel better to do that, that's no problem. But for me, I'm not going to do that. I'm just going to assume that r is r, and whatever the value of r is, you'll see that it actually will cancel out eventually when you compare the area of the pentagon to the circle. The key to this question is drawing the picture correctly. So I'm just going to draw the pentagon inside of the circle. So let's count to 5 here. That's not the best pentagon ever, but I'm just going to draw that. Now let's take a look at 1/5 of the pentagon. So for example, let's take out this triangle here. So if we can find the area of this triangle, then the area of the triangle times 5 would be the area of the pentagon. So we're starting to build up like a little story here, right? So here, the area of the triangle is going to be something. And then the area of the pentagon, I'll just say pent for pentagon, and it's a regular pentagon, is going to be 5 times the area of a triangle. And of course, the area of the circle, hey, I'll put a 0 for the circle because that looks kind of cool. That's easy, you know the area of a circle. That's pi r squared. And finally, we can do the actual fraction. So I'll just say here the answer is going to be area of pentagon divided by area of the circle. So you can see here that it's going to be something over pi r squared. So that's kind of like the top-down look at the actual question. So what I want you to do now is think about how we can get the actual area of the triangle. Well, let's affix some information to the figure related to the circle. So this line here in blue is r, and so is this, because they're radii of the circle. I'll just tick them off like that so that you know that it is actually an isosceles triangle. Further to that, why don't you take a moment and think about what the angle is in here. Can you think of that angle? Well, that angle, I can give it a name here. I'll call it theta. That angle on the side here, theta, is going to be somehow related to 360. So let's take 360 here. Remember, 360 is 1 revolution. See, 1 loop. Well, that's not a full revolution. What fraction of a revolution is it? Well, if there's 5 triangles, you're chopping it up into 5 pieces, so it's going to be 1/5 of 360. So 360 divided by 5 is 72, and that's in degrees. So now we're starting to really understand how this is going to work, because we have the information to write the formula for the area of the triangle. You should note that it doesn't matter if you knew what the actual value of the radius is, because it will cancel out. But you do know that you have a situation where there is a contained angle. So if you don't mind, I'm going to go really fast to the beginning of this presentation. And where is that formula? There it is. That's the one I'm talking about, okay? You see? You have a side, and an angle in between. So I'm not going to do those flashbacks anymore. That's just one time only today. So I don't want you to get dizzy. Anyway, we're going to use that formula right here. See? Half. And the two side lengths are r. They're the same. You could put r squared there, but you know what? Nobody's chasing us here. And that's sine of 72. And that's in degrees. Of course, you could write that a little bit nicer. That's r squared sine 72 over 2. Got to be careful with my degree symbol there. Okay. We can also just go over here now and multiply that by 5, because the pentagon is 5 times this quantity. So I'll just write it out again. That's 5r squared sine 72 over 2. And that's it. You got it now. So we're going to I'm going to do a little copying and pasting here. So that's the numerator of our fraction. Looks like I lost the degree symbol. That's okay. I can recover it after. Whoops. I'll do a little bit of housekeeping here in a second. Looks like I defeated my whole technique, but that's okay. So there's pi r squared. And let's just put back that degree symbol. So anything clean up here? Do you see that? The r squared disappears. So it doesn't matter if you make this assumption over here, because whatever number you choose for r, even something strange like 2.9, it'll still just cancel out. It'll be 2.9 squared, but it'll still cancel out. So let's clean this up here. So that's 5 sine 72 over 2 pi. I've noticed that through your assignments you are very aware and competent about how to do calculations. So I'm not going to drag this one out. I am just going to write that as a percentage. I did this earlier, and of course it is the correct answer. This is going to be 75.68%. So it's roughly 3/4. So if you guess 3/4, it's not bad. Good job. So let's see if we can take this example, part A, and kind of leverage it into part B. What I'm going to suggest is that we just copy and paste the entire answer here, and I'm going to do a little bit of housekeeping on the next slide there to see how we can optimize our time together. So I've pretty much copied what I needed. Oops, there it is. Okay, so this is the octagon. So let's get rid of this circle here. And I'm not looking for artistic points, but I am going to delete anything in the answer that involves the 5 or is derived from the 5. So no 72s. So those 72s are all gone. The answer definitely changes. That's gone. The 5s are going to change in a minute. So let's just draw the circle here. If you want to draw an octagon, honestly, the cheapest way to do it is think of a stop sign. So a regular octagon, I should say. So I just do that, and then I can frame it nicely. So that's like the cheap way to do it. And let's draw that triangle in with RR for the 2 radii. And the angle that I want to figure out is theta over there. So theta this time is going to be 360 divided by 8. And that's 45 degrees. So anywhere that I had 72 before, let's put a 45 instead. I'm not trying to be cool here and show off, but I am trying to show you how to think smart. And I'll just say oct for octagon. Trying to show you how to do things a little bit creatively, because it's nice to take advantage of the technology that we have. Now those 5s have to become 8s, because there's 8 triangles that form the regular octagon. So those 5s all become 8s. And the full 45 degrees have to appear. Alright. And we got 45 there. And of course, 8 divided by 2 does reduce to 4, but I'm deliberately leaving it like that because I want you to compare how one looks to the other. So I'm just going to double check that everything looks good here. And I think we're good. If I made a little mistake anywhere on the pasting, I'm sorry, but I think it looks right. So I don't rehearse my presentations. I should just tell you that off the bat. But I'm very strict about hopefully getting the right answers, because that's pretty important. So that's the answer, 90.03. So although not for your assignment, you might be wondering what would be the formula for a regular, and it would be n-sided polygon. So maybe that's something that's interesting to you. What would be the formula for that scenario? Now, I do have an answer, but you know what? I don't see many comments in the video, so I'm going to leave it to you as a challenge and put it in the comments. And if anybody gets it right there, I'll be a good detective and make sure that I look through your comments and tell you what the formula is. I'm sure it's readily available online somewhere. So here's the next example. This is a take on the example we had in the previous lesson, except in this situation we have 3 angles of elevations that are somehow related to some length calculations. So ultimately what we're trying to find here is the distances ABC, and these are relative locations from 3 vantage points. So imagine that someone's standing here, and someone's standing here, and someone's standing here, and collectively the furthest person is 90 feet away from the base of the building here. And the question is, what are these relative distances? And it's amazing that, or it might shock you, that with just 3 angles of elevation, which you can measure them from any distance, that's sufficient to calculate this. In order to facilitate the answer to this question, it's recommended that you first calculate the height of the building. And of course, please feel free to call it h, and try the calculation, pause the video. This question definitely would be, I would consider it a medium level question. It's not anything specifically hard about it, it's just a lot of writing. So what I'm going to do for this one here is I'm going to write the formula that I use for each calculation and just write the answer. So if that is okay, I don't want to drag this one too long because the video will take forever for you to watch. So let's go back to the actual clear diagram here. So the strategy that I'm going to use here is to find the height first, and then I'll start to eat into the actual bases here. So let me just say in order here, I'm going to get H, C, and then I'll get A and B at the end. I'll just say CBA. You can do CAB as well. So we're going to go reverse alphabetically. As we do each step here, I am going to highlight the figure differently. So how might you get H? Well, H would be gotten by just looking at the overall triangle here. So that's a right angle triangle, of course. We can use the 90 feet at the bottom here, and we can use the 38 angle degree here. So if we use the ratio, it would be tan. So that'll be tan of 38, and that's going to equal h over 90. Once you have h, then it really unlocks the question. So what I'm saying is I'm not going to show you the intermediate steps here because we really grinded that out in the past videos. Instead, what I'm going to do is just go after the final answers to 2 decimal places. So h is approximately going to be 70.32. If that is something that irritates you, I'm sorry, but definitely I'm forcing you to think a little bit more aggressively now with the calculations. So at this point, you could actually just draw 3 triangles if you want. That was the big one was the green one here. But you can just also draw the middle and the small triangle and work your way in. So we're going to actually go after the 58 degree angle triangle. I'll do it in orange here, because now you know what the height is. You know this guy right now. So we can see that that's also a tan ratio. I also mentioned in the previous video that tan is all over the place when it comes to construction questions because it's related to slope and angles of elevation. So we're going to have here tan 58 is going to be h over c. But we know what h is. H is 70.32 over c. Remember in the previous video we would switch these two terms and divide the answer. So I'll just state what the answer is for c. I got 43.94. And that's in feet. I'm trying to be very careful with my approximate equal signs here. So that's done. Now it's a matter of getting a and b. The last step will be the easiest because if you have two of these, then a is easy. You just do 90 minus. So I'm going to go after the middle triangle now. I'll keep the h highlighted in orange there. Let's go with purple this time. So if we take the 48-degree triangle here, we can actually write tan again. I'm going to write this one over here. So tan of 48 is going to be h, which we know is 70.32. And that's over b plus c. We know what c is, but I'm just going to write b plus c for a second. The reason is algebraically it's a little bit easier for me to do a little switcheroo here. So what I want you to do is switch this guy and this guy, because algebraically that would be equivalent to a step that would precede a cross multiplication. So in this case it would be b plus c. That's looking a little bit gross, sorry. Equals 70.32 feet over tan 48. And now it starts to unravel. So we have here b equals 70.32 feet over tan 48 degrees. And now you're going to take the c here and you're going to move it to the other side. So we're going to do minus c. But we know what c is. C is 43.94. So we just drop that in there. So what is b? B is going to be 19.37. And that's in feet. So we're starting to really make some progress because the question virtually is done. Because the last part of the question is just your basic subtraction. Why am I highlighting the answer for h? Well, more so just to have you have a reference there. Let's finish the question off. So I'll try to stick to less colors next time. Anyway, the last step of the question is just to use the 90 feet. So I'm just going to say here, use 90 feet. And I'll just do that. And I'll just state the answer for A because I'm pretty sure you know how to subtract. Anyway, A is going to be 26.69 feet. So 70, 26, 19, and 43. See? 70, 26, 19, and 43. Notice that it's a 38 here, and here it's a 37. Don't let that annoy you. The reason is that my answer, I kept more digits in the intermediate calculations. So if your answer is off up or down by one number at the last digit, it's not a big deal to me. And definitely would be very lenient in terms of marking such an error. Time for some algebra. This question here, there's nothing really profound about it. We did something similar to it in the previous unit. In this case, I'm just trying to make sure that your algebra is up to speed here. So we're just trying to solve for the length x, and then ultimately you're trying to find actually the length of the vertical side. See, a trap that you might fall into is that, hey, you know, I solved for x, I'm all good. But the question is not asking for x. X is a stepping stone. We're actually looking for this. We're looking for the height. That is our goal. So make sure that you will keep your goal in sight so that you answer the prescribed information. So let's do some algebra. I know this is h here, and I'll get to that later, but the main thing I want you to figure out is x using the appropriate trig ratio. So it's a right angle triangle, and that's adjacent and hypotenuse. So I'm just doing the labeling here. Adjacent and hypotenuse is cosine, so we're going to have your cos 31 is x over x plus 3. I would like to take some extra detail into this answer because it's a pretty good practice. Now, I'm going to put lots of decimals here. So that's 85716 approximately. And that's x over x plus 3. Let's cross multiply there. So that's 0.85716 times x plus 3 is x. I should line up the equal signs, but hey, it's all good. We're near the finish line together, so let's not get too grumpy about small stuff. So that's 0.85716. Some people accuse me of my 8s looking like 6s and vice versa. So I got to be careful there. So what am I doing here? I'm taking this decimal and I'm going to multiply by x. So that's just going to be literally that number times x. But then I also have to multiply by 3. When you multiply by 3, you're going to get 2 point something. So that's on my calculator here. 257 151 I got actually. My stylus is a little frozen here, sorry. And that's going to equal x. So a matter of this point here, I should put the x here. We're going to move the terms over to one side, all the x's. So this x is going to go on this side, and this decimal is going to go on the other side. So we end up with 0.85716 x minus x is negative 2.57151. Notice that there's actually a 1 in front of the x, so you're going to do 0.8 minus 1, which is 0.14 something. I grabbed my calculator and I got negative 0.1428. So it's just an algebraic marathon. And if you divide both sides by that decimal, you're going to get the answer that you need. And x is going to be 18.00. So it's pretty damn close to 18. And that's in meters. I think the question is in meters, it said. That doesn't solve the question completely. We still have to find the height. But if we go to the diagram and put 18 in for x, I'll do that in green here. So this side is, whoops, I got ahead of myself. That's 18 meters. It's 18.00, but I'm being lazy with the zeros. That's x plus 3, so that's 21. So we can just find h using the Pythagorean or with tan. So I'll use the Pythagorean theorem. So that's going to be 21 minus 18 squared, squared, and square root. I think in my personal solutions I actually did it with the tan function. So I got 10.82 when I did that. And that's in meters. So that's the height or the length of the vertical side of the triangle. In this example, the calculation, the algebra, is very similar to the previous one once you set things up. So I'm going to set up the actual formula that we're going to use to solve in this question, and then I'll leave some of the algebra to you to try, okay? So anyway, the question here is that we have a circle that is tucked in nicely into this angle, and we want to draw or find, the radius of the circle. We know that the distance between the closest point on the edge of the circle or the arc of the circle in P is 5 meters. We also know that the angle contained here by these two line segments is 64 degrees. So the question is to solve for that radius. This question it could be applied, for example, let's say you're fitting pipe into a cross section where the cross section of a wall, for example, is not that rectangular, to say the least. So, like with other questions we did in the past, can you figure out where a triangle could be located? This pattern is familiar to you because we covered this, I think, a couple weeks ago. So we know that the radius of the circle here, r, and I'm going to just erase this one here, so see you later. because it actually is kind of deceiving to have that one there. There's nothing wrong with it, but it's a little bit easier to follow now, isn't it? The radius and the tangent, this is a tangent, is 90 degrees to each other, and are 90 degrees to each other. So in this case, we can just bisect the angle 64 and construct that right angle triangle. So let's take a look in terms of the actual calculation here. So we have a right angle triangle. This is R. This angle here, well, that's 64, so this is going to be, due to a bisecting angle theorem, that's going to be 32 degrees. And this length here at the bottom, we have seen this before, it's going to be R plus the extra 5. So what's R plus 5? Well, it's literally R plus 5. So we're going to apply the appropriate trig ratio. Is it going to be sine, cos, or tan? Take a moment to think about that, and then we'll just do the algebra, or at least set it up. So in this case, we have opposite and hypotenuse. So that's sine. So sine 32 is going to be R over R plus 5. You know what's funny is I remember in class doing this one time and just throwing out an answer that was extremely close without cheating or anything. And the students are like, wait a second, sir, how did you get the answer so damn fast? Or at least it was close enough. And my response was that I knew that sine of 32 is roughly a half. So I just had an idea that this fraction should be roughly a half. So I ballparked it at 5 or something. And the answer obviously was more close to 6. It was 5.6. But I didn't actually use sine of 30. I did something a little bit more creative. Anyway, how would you solve such a question? Well, I'll use less decimals than the last time. But you would have 0.5299 here as approximately what sine 32 is. And that'll be R over R plus 5. I'll cross multiply. And then after this step, I am confident you know what to do. So I'm just going to do a little bit of writing and not talk as much, okay? Let's go through that. So distribute. I was going to just leave it for you to try on your own, but I guess I'm going to write it now. Actually, I think you can finish this one off. So I'm going to take this number here, move it to the right. I'll take this quantity R, move it to the left, and simplify that by collecting the like terms. So you're going to get here negative 4701. R is negative 2.6496, and that's 6. And then you can just divide both sides to get the final answer. So that's 5.636 meters. And that's it. So we'll see many more examples today. I think at least 4 more that involve circles and some really strange diagrams. So this next example involves some calculations with sine, cos, and or tan, although some people may try to use similar triangles for a big chunk of the solution. I'm just going to stick to the trig ratios here though. So the idea is that we have this line segment, which is AE here, and we want to calculate its length. But all we're given is the dimensions of the rectangle ABCD and an angle down here of 70 degrees. So the answer is here. This one here is a nice one to try on your own, and definitely one that without any prior knowledge is going to stump quite a few students. So I'm going to go through the solution, and it'll involve some coloring. So what I'm going to do here is I'm just going to color a couple of triangles here. So this guy over here, I'm going to make it orange, or at least what I perceive to be orange. And over here, we'll call this one the yellow triangle. And what we're going to do is try to calculate some information within those triangles. So if you're kind of stuck and you're like, you know what, I don't know what to do some easy stuff. You know, it's like when you want to work out or something. You always warm up. So here's some warm up for your brain. That's 20 degrees because it is a rectangle. This is 90, of course, overall. And that angle there is 70 because there's a right angle up here. Also, if you want, there's a Z law. See that Z law? Two parallel sides, and then it crosses over like that. So those are both 70, referring to these numbers here. Just something to think about. Okay. Over here we can migrate into the next triangle, and that's a 70. And of course they add up to 180, so this has to be 20, or I was going to say 90 minus 70, or 20. Now, in order to facilitate my answer, and again, I'm not using similar triangles here, I'm going to call this length here y. This top edge from here to here, I'm going to call that y. So take a moment and think about what this length would be. Remember that the bottom length is x, so it's the leftovers if you subtract y. So that's 8 minus y. So now we have the orange triangle and the yellow triangle, and we can do some calculations. Ultimately, if you can figure out what y is, that unlocks this question, because then you can go to this triangle and use SOHCAHTOA to get x, because you would know what this is very quickly. So let's try to calculate y using the yellow triangle. So perhaps I'll just do some yellow here. Okay. So I used the tan ratio, and I did this. Tan of 20 is y over 5. So where's that coming from? Well, I know this is 5 here because it's 5 over there, and that's in meters. So tan of 20 is opposite over adjacent, and that's how I did that. So if you do this calculation, you get 1.8199 meters. So that's the yellow triangle. Let's go to the orange triangle now. I'm laughing because it got very colorful today. So anyway, we know what y is, so we can actually go and get 8 minus y. So 8 minus y is 6.1801. Whoops. So now you know that this length here is 6.1801 meters, of course. Let's put some meters in here. Just in case you're fast forwarding the video, let's make sure the real estate looks good. We can now use the trig ratio over here for calculating x. So I'm going to use the sine ratio on the 70 degrees. See, opposite over hypotenuse. So let's do that here. So sine of 70 degrees is x over 8 minus y, but 8 minus y is now known. It's 6.1801. And just multiply those together to get x. So x is going to be approximately 5.807. I remember in one semester, although you don't have any tests with me this semester, our course is exclusively based on assignments that progressively get harder as the semester goes by. I do ask on a past test for students to create a formula where this is length and this is width and this is theta. So I do challenge students to get a formula there. Quite the challenging question. A lot of fun. In this next example, we're looking to calculate the area of a regular pentagon when we're strictly given just one of the edge lengths on its perimeter, in this case 7 meters. So it'll be shocking to some people that you would only need that to calculate the area. I would pay attention to this question closely because I do ask you in your assignment to do a similar question, but I do apply it to a real life scenario where I actually give you the information about the Pentagon, that is the building in Washington, D.C., and I ask you to calculate the area of that building, at least within the borders of it. Not the floor area, because there are open sections, but the overall area. So anyway, let's try to calculate this area, and let's do it quickly because it's not that long of a question, and we do relate this to the first example I covered. So what you want to do here is find the area of one of these triangles, and once you have one of those areas for the triangles, then you just multiply by 5. So let's take a look at this triangle here. I'm going to draw a right angle triangle immediately. Actually, I'll draw the overall triangle, but I'm only looking for the height right now. So I'm going to call that H. So let's just highlight half of it for a moment and talk about that. So let's use this yellow triangle to calculate the height of it. So what is the angle up here? Well, that angle there is going to be 1/10 of a circle, or 36 degrees. If you want, you can say that this is 360 divided by 5, which is 72. We saw this earlier already. And then half of 72 is 36. We also know that this is 3.5 meters from here to here. So we could use a tan ratio. Good Lord, lots of tan ratios today. And we can get H. So we have here tan of 36 is going to be 3.5 over H. And you can do a switcheroo there and solve for H. So H is going to be 4.8173. Lots of extra digits. Okay. Now we want to do the overall area calculation. So what I'm going to do is I'm going to refer to the entire triangle now. And we're going to find that area. Let's just call it a triangle. I can even use the same color scheme as the first example. We can find the area of one triangle, which is half base height. And then we can find the area of the pentagon. I'll just say pent is 5 times the area of the triangle. And I'll put my final answer right there and put a box ready to go. So let's go through that. In this case, the base of the triangle is not 3.5, it's actually 7. It's the whole thing. And of course that's 7 meters. So the base is 4.8173 and the height is 5. And when you compute that, you should get around 16 or 17, I think. I'm just going to check it on my calculator. I got 16.861. The units are in meters squared. And multiply that by 5. Now 16 times 5 is 80 and 0.8 times 5 is 4. So it's around 84-ish. Check it on my calculator. I know it's 84 point something. So let me just type that in for a second. Okay, I got 84.30 meters squared. Just going to double check. Okay, so it says 84.31 in the notes as well, but if you're up or down by a digit, we're good. I like to keep more digits than the author of this particular set of notes. So yeah, that's a nice little pentagon calculation. Everything else in this video is circles. So hopefully you like circles. So this next example really is one on the trickier side, and it does involve some calculations with circles. The last few questions that we cover all exclusively involve circles, but this one here, the sector of a circle is used specifically. So what I'd like to do is just kind of walk you through the procedure. So it says here that the curved arc here, BC, is part of the circle with a radius of curvature 1.6 inches. And if you're wondering what that means, is that imagine that you actually had a sector of a circle, like a pizza slice if you want, or a piece of pie, literally, that this radius, whatever that I'm ticking off here, is 1.6 inches. I promise you a better diagram on the next page, but the question is to find the area of the shaded region. So it's kind of a bookkeeping nightmare if you don't really get yourself organized. So I've just drawn the diagram there, and you can see that I've actually augmented the figure with the radius. This diagram is not to scale, so please forgive me for that. But what I want to say is that from here to here is the same as from here to here. And that's the radius. And that radius is 1.60 inches. And you can see, of course, that I have not done a good job with my scale, but I needed to exaggerate the figure so that I could fit my annotations nicely. So that length there, can you see how much it is? Well, if this is going to be 1.6, you got to take away the half, and that leaves you left over 1.10 inches. So in order to answer this question, I'm going to just kind of do a little bit of cleaning here. I'm going to just give myself a little bit of room here. And we're going to start labeling the figure. Now this region here, divided by the borders of the actual shapes, this is A1. I'm going to call that area 1. This curved area here that is just part of a circle, it's not a cap, but it's part of a circle. That area, I'm going to call it A2. So A1 and A2 together would be the rectangle. And that's easy. That's just 1 times 1.5. So it's going to be 1.5 square inches. Now, there's a right angle triangle below here, and that triangle, I'm going to call it A3. Finally, to facilitate the calculations, I need to define a variable here for the angle. I'll call it the ever creative theta. What I need you to do first is, if you like, pause the video, and based on this annotation, can you figure out how to get the area 1 there? And of course, if you can do it under 5 minutes, you're pretty good. So there, take some time and try it. Okay, assuming that you have unpaused the video, let's go through the calculation. What I'd like to do first is actually get the angle theta. So I can use cosine on this triangle here. So cosine of theta is going to be 1.1 divided by 1.6. And we get theta is 45.56. Okay, now that you have theta, you can go and get some areas. I'm going to go with the area of the triangle. So the area of the triangle right here, let's just keep it highlighted for a bit. That area 3 is actually going to be, the easiest way to get it is with the contained angle. Like, you could find the top edge here using Pythagorean theorem or sine, cos, or tan, and then you could do base height over 2. But a more economical way to do it is just to do the contained angle. Because remember, theta is contained by those two sides, so it's that other formula that I've used a couple of times today. That's half 1.1, 1.6 sine theta, but we know what theta is now. So that's going to be sine of 45.56 degrees. If you do that, you're going to get an area 3 of approximately 0.6390 square inches. Okay, for the sake of space, I need to squeeze some of my calculations here. So let's just do that. Hopefully you can still read that. Okay, so that's area 3. So that's kind of like phase 1. If this question was out of 10 on a test and you got this far, I'd probably give you like a 5 or a 6 maybe, because you're getting pretty close. Probably a 5. Anyway, let's go after another area. So now we're going to do the area of the sector. So by sector, I am referring to this yellow region. So that sector involves A2 and A3. So I'm going to say here A sector. Alright, so I'm just writing down the formula here. That's theta over 360 times pi r squared. And the, actually I'll just put r squared here. We know that the angle is 45, and we know that the radius is 1.6. So we have here, sorry, did I say 46? That's supposed to be a 46 there. Whoops, sorry about that. Anybody was troubled about that, I'm sorry. That's 46.56. I read my calculator wrong. and the radius is 1.60 inches. So I'm going to just calculate that on my calculator there for a second. Okay, I got 1.040 square inches. So that's the area of the sector. So it's looking pretty good. We know if that the area of the sector is the sum of A2 and A3, and we already know what A2 is. So I guess we can just go and we already know what A3 is, so we can go and get A2 now. So I'm just going to do that now. So here we go. So A2 is equal to A sector minus A3. So I'll just annotate it nicely here. A sector. So that's 1.040. I should have kept an extra digit there. I should mention that I do keep extra digits on my calculator, so don't worry about that in terms of my reliability with the answers here. So that's well, you're gonna have to round to 3 decimal places here. I should round to 3 decimal places because of the precision. We're limited by 3 decimal places in the precision. So when you subtract, you always go with the weakest precision. So that's 0.401 square inches. And look at that. We know A2. So I think we're laughing now, or you should be happy because the answer is essentially done now. If you want the area of 1, just take the area of the rectangle minus A2. And the rectangle area is going to be, well, it's this times this. So what's 1 times 1.5? So it's 1 times 1.5, so it's 1.5 square inches minus 0.4, and that's accurate to the desired precision that we need. And this is 0.401 square inches. So the area of the shaded region, final answer, I got 1.099. So that's probably the longest answer, apart from the triple angle of elevation question. This definitely is a nasty little question. So in terms of how much you have to write. Okay, so before we do the next few examples, I'm going to just show you one more piece of theory in terms of a special relationship involving a 45-degree isosceles triangle. And this ratio comparison will be used because it's very common when dealing with circles and geometry. The idea here is that if you have a square, and let's say the square is A by A, and you draw a diagonal through the square, you should cut out an isosceles 45-degree triangle. See, that length is the same as that, and there's your right angle. The key thing here is that whatever the length A here and whatever the length A here is, it doesn't matter. The diagonal will always be A times root 2. So we're going to use this pattern. Now, there's the formula right there. We're going to use this pattern in many questions coming up, actually 3. Just to emphasize this a little bit here, let's say you had some numbers. Let's say this was 7 and 7. So there's your isosceles right triangle. The hypotenuse will be 7 root 2. So you just multiply by root 2. So the ratio is always 1 to 1 to root 2. What if it's not 7? What if it's some nasty decimal like 4.3? Well, you just put 4.3 root 2, and whatever that decimal is. For the next few examples that I cover with you, you can solve them exactly by using the root, 2 I should say, or you can do them approximately and just write root 2 as a decimal. So root 2 as a decimal is roughly 1.414. So let's just see the examples that I cover here, and you can decide how you want to answer them. You will get a question on your assignment that does involve this triangle. Okay, so here's the first example. It's question 14. And this is 14 out of 20, so you can see that we really dusted a lot of the questions in the notes now. The idea is that you want to find the largest diameter D for the pipe that can be fit into this quarter circle. So imagine this is a cross section of a wall, and you want to fit a pipe through it. And the cross section is a quarter of a circle. So I've given a hint here about how to do it by drawing these dotted line segments. What you do know is that the outer quarter circle has a radius of 5 inches. So it's not a lot of clearance. But these types of questions are very, very comfortable in terms of plumbing and HVAC type disciplines. But it doesn't matter what program you're in. I do believe that in general, in construction and related trades, you should know how to do calculations with circles. So let's take a look at that diagram. Again, we're trying to find the diameter of this circle. It's very common in these questions that the diameter is asked for. But you know what? If you can find the radius, just double the answer after, and that should be fine. So let's take a look here. I'm gonna do some annotation here. I know that from here to here, I know that is a radius. I'm gonna call that R. I also know that this is a radius, R, and that's a radius, R. So using the pattern that I mentioned earlier here, I have R, R, I'd have R root 2. And that's exactly the pattern that I'm going to do here. So that diagonal there, keep in mind this is a square, that's R root 2. And then you can draw a simple comparison to the 5 inches. See, R plus R root 2 should be the same as 5. Why is it the same as 5? Because everything I'm drawing right now is 5 inches. Because it's a quarter of a circle. So let's just reveal those annotations a little bit nicer. And we just compare the two quantities. So we have the 5 inches. Let's just write down the R plus R root 2 first. So R plus R root 2 is 5. And that's it. If you convert the root 2 to a decimal, this answer will not take you very long. For the students that feel comfortable with roots and such, try to answer the question without touching your calculator at all. See if you can get the answer in the back of the book. It's pretty gross. It's 10 root 2 minus 10. Or if you factor out the 10, it's 10 bracket root 2 minus 1. That's the diameter. That's the diameter D. But I'm not going to solve it exactly here. I'm just going to solve it approximately using decimals. So I'm going to put here R. Now root 2 is 1.414. So I need an extra digit on that. In my engineering background, I know root 2 to 3 decimals inside out, but I don't know it beyond 3 decimals off by heart. So that's 1.4142. And that equals 5. So then you would have 1 of those plus 1.4 of those. So that's 2.4142. R equals 5. You can divide by the 2.4142. And if you do that, let's do that here. I'll add 1 on my calculator and do 5 divided by that. And get 2.0711. 2.0711. This is in inches. I should put inches here. But I'll write it like in full word here because the inch symbol might look like an exponent to somebody. So anyway, that is the radius, and it's virtually cosmetic to get the diameter now. Just double it. So I'm not going to give you a wacky explanation there. I'll just double it on my calculator. And 4.142 is the answer. Sometimes trying to guess the answer is not that obvious, but you can see here that the answer should be less than 5 inches. There's no way that you're going to fit a 5-inch circle within a quarter circle of 5-inch radius. So it's going to be, it has to be less than 5. Anyway, that's the first one. Here's the next one. This time we have two circles of equal size that are contained in a square. And the idea is that you want to find out what the diameter is of either of those circles. This answer here is going to be very similar in style to the previous one. Just going back to the previous one, that's the equation. It's not that bad once you figure out the equation. And for this one, it'll be something similar. Once you set up the equation, the answer to get to the end there is not that bad, the method. So take a look at the picture, nice and big here. And let's just start putting radii. So that's the center of the circle, that's the center of the circle. If I don't get a straight line, it's okay. But it'll be good enough for a freehand. So here we go. Whoa, almost had it there. Not bad. What is the length of that purple line? Well, if you look at the outer dimensions of 2 and 2, this should be 2 root 2. So we know that the overall length of the diagonal is 2 root 2. So I'm just going to put 2 root 2 right away and get that out of the way. And then I'm going to get rid of that. Now let's break it up into steps. Every line segment that I draw right now is going to be of length r, where r is the radius. So that's r, that's r, that's r, that's another r, and that's another r, and that's another r. And I got tired, not bored, of saying all those r's. Furthermore, you can do the 1 root 2 trick. So this length here is r root 2. And this length here is r root 2. So if we tally them up here, we have this guy, and this guy, and this guy, and this guy over here. They add up to 2 root 2. So let's just state them, and we have an equation. So we have r root 2 plus r plus r plus r root 2. And these are all converted to decimals if you like. Remember, that's 1.414, and so is that one. And then these are 1 and 1. So if we connect them all together here, we get 1. I'll do it as a root 2 on my calculator again. So we get root 2 times 2 plus 2. So this becomes 4.8284. And then 2 root 2 is 2.8284. Now, I'm not shocked about that because the number calculations are very close to each other. Lots of patterns here. So if we divide the two sides by 4.8284, we should get the radius. And that's 0.5858. I'll put it as 0.586, that's fine. And that's in inches. And then the diameter, I used a lowercase d on the previous question. I'll use an uppercase D here. I try to be very careful with my annotations in terms of, and also my consistency with how I write things. Because, you know, it doesn't look good. Okay, so we get D is double that. So that's 1.172. The program glitched there for a second. It's just, I think my computer is saying, your file size is gigantic, John. You gotta calm it down. In this next example, we'll just look at one more situation where you can use the 1 root 2 trick. Pattern, I should say. So the idea here is to find the largest diameter D that you could fit into this region. Now, perhaps, for example, maybe this is someone's backyard and this is their deck, and you wanted to say, well, what's the largest circular pool that I could fit? Or maybe you're fitting a pipe through a cross-section of a wall, but when you look at the cross-section, this part here is some type of a support bracket, and you can't really access that part of the cross-section. So then this could be like the conduit, like an air duct or something. Anyway, let's get at it. Firstly, look at the outer border, and it's a 2 by 2 square. So then, just like the previous example, that length there in purple is 2 root 2. In this case it's meters, but it's still 2 root 2 in magnitude. Now you want to chop it up into smaller line segments. So we can do the following. Break up some radii here. So that's r, r, r. We saw this already a couple times. And this length here is r root 2. So this length plus this length plus one more length to be determined, this one over here, should give us 2 root 2. I'm going to just clean it up a little bit here. So what is that length? I want you to imagine a small square right here. What are the dimensions of the square? Well, I'll just draw it down here as well. This is 0.5. This is 0.5 because it's half of the 1 meter here. And the diagonal should be 0.5 root 2. Yeah, that looks kind of gross, but that's what it is. So I'll put that over here. I'll just put 0.5 root 2 right there. So 0.5 root 2 plus r root 2 should equal that. So 0.5 root 2 plus r root 2 equals 2 root 2. And yeah, that leads to some pretty routine calculations, hopefully. So this is 0.7071. These are all in meters. R is just r. I'll put these together. So r plus r root 2 is 2.4142. And that's r. And then 2 root 2, of course, we saw that earlier, is 2.8284. So just take the 0.7 and move it over to the other side, and then divide by this, and you should get the radius. So I'll spare you that calculation because this video, I haven't tallied up the video yet. I recorded it in pieces today, but I'm pretty sure it's the longest one I've recorded for you this semester. So anyway, r is approximately 0.8787, and of course if you double that, you'll get the diameter, and the diameter to the prescribed precision in the question, which I believe is 3 decimal places, is 1.757 meters. So that's that. And the last question. So this is the last question you're going to get from me this semester. In my opinion, in the book, this is out of the 20 questions, this is top 3. So I'll tell you a little story there. When I first started teaching at the college, the author of this book had brought me into the college to teach for my first semester as I was writing on my PhD. So anyway, he hands me the book and he goes, teach this to the section when you start in January. So I'm like, oh, I'm so good at math, I can do this, no problem. And then I looked at this question, I was like, how the heck am I going to explain this to this example to people in an economical way? Because my solution was honestly gross. But then thank goodness I came up with something creative and it made it a lot easier. So the idea is that we have 3 circles of equal diameter and we want to fit them into an equilateral 2 meter by 2 meter by 2 meter triangle. So the question is find the exact expression and also the approximate expression. You can see that it's going to be 0.732 meters. Now, I'll leave the exact calculation to you as an exercise, but I'll show you how I solved it eventually, and I found some really wicked, glorious way of doing it. Super, super easy, because you're probably getting scared when you look at this question. So anyway, pause the video and see what you do. Okay, if you got the right answer without any assistance and you did it in under, let's say, 10 minutes, that's pretty good. So I'll show you how I solved the question. It's going to involve a little bit of fun stuff here. So what I'm going to do is I'm just going to actually zoom the figure even further and get my magical eraser here, or fake eraser. So I need to focus on the corner of the figure down here. Now, I'm going to just draw a triangle right there, because that's all you need to solve this question, this purple triangle. So let's talk about some calculations. Firstly, what is the angle here? How much is that angle? It's an equilateral triangle, so that's going to be 60, because it's 180 divided by 3. If you cut the triangle in half, then they're each 30, because it's an angle bisection. So this angle here is 30 degrees. I hope you can see that. 30 degrees. Next, you know what? I'll just do this. I'll put an arrow, and I'll say divide by 2. That's a 2. Okay. Next, that's a radius. If you can figure out the base of this triangle, or at least relate the base or the hypotenuse to the radius, then you can use the algebraic method that I showed you earlier when we bisected an angle in terms of this pattern. We saw this earlier today already. Well, guess what? There's hope. What is this length here? Well, that's 2, right? So what's half of it? How much is this length? Well, that's supposed to be 1, right? That's 1 meter. So I'll just do that. Oops, overshot it a little bit. So what is this length over here then? Let's do it in green. What is the length from here to here? Well, the key is that the radius of the circle extends to here as well. That's r. So if we take 1 and we subtract r, then that's what this length is over here. So that's 1 minus r. This is really squeezed, but I will draw it up here nice and generous. Okay, so 30 r and 1 minus r. We've done calculations 2 times already with questions like this in terms of the algebra. So I'll set it up and I'll tell you the answer, because I am confident that if you did the other ones, that this one is just as nice. So what you would do is type that on your calculator, whatever decimal that is, and then you would cross multiply and eventually solve for r. So I am just going to state the answer here. R is approximately 0.366. And then, of course, the diameter is double that. Now, you can double that pretty well, I hope. So that's 0.732. And that, people, is the final answer. So yeah, that question gave me a little bit of a headache and under pressure to present it to a class. But you know what? When you do enough math contests in life, as I did back in the day, it's good to keep your brain sharp. So anyway, let's talk about the second half of the semester. It's really important that you understand that after this assignment this week, my connection to you as your primary teacher is shifting to Jesse, who is the teacher for the second half. So Professor Vadut is going to cover the second half of the semester. Now, there might be some small differences in how it's treated, but it's still going to be assignments every week. And when you go to the end of the semester, you'll have written 11 assignments potentially, and the top 10 will count. So in terms of delivery, there may be slight differences in how it's done, because the professor really has their own style in terms of what works for them and how they feel they can give you the information best. I really hope that you had a good time following the material that we've done together. I've had some very good emails, some very good feedback from you, and I've been constantly trying to improve on what I am doing with you in order to make your experience as positive as possible, especially under the constraints. So, for those of you that are considering going into the degree program at the end of your diploma, I highly recommend that you keep on watching the videos that I have here, because I will be teaching the degree mathematics course in the fall. So I will be teaching a course called Math 1151 in the fall. This is a course that is going to involve calculus and other stuff. Although you won't be registered in the course unless you transfer to the degree or apply outside the program again. It's really a good course that you could follow, and I do intend on putting information on YouTube there. And I'm going to put a lot of other math stuff on YouTube. So please, if you like what's going on here, keep in touch with my content, because I'm not doing it for any other reason except to help out the student body and those that don't have access to tutors. All right. Thank you so much for the semester. I wish you the very best. And yeah, have fun with this last assignment, because it's a good one. Take care.